Good afternoon, everyone. Thanks for coming to our talk. Let everybody get seated for a sec. Thank you for being here. We're excited to give this talk. This is the first time we've given this one externally. Debugging etcd is a big part of our daily jobs. It's something that we care a lot about, constantly trying to get better at. We do it both to solve customer issues in GKE and keep their clusters healthy. And it's also important so that we can get to the root cause of issues, and I mean the real root cause of an issue in etcd, so we can fix it in open source and make the software better for everyone with each release. And that's where the community, all of you, really come in. We'd like to share our learnings with you and our experiences to enable you to be more effective at keeping clusters healthy and also maybe contributing back to the projects. My name's Joe Betz. I'm a Google engineer. I work as a maintainer on the etcd project, and I also contribute to Kubernetes. And joining me today is Jingyi, who is also my colleague and an active contributor to both etcd and Kubernetes. We'll start the talk today with a brief recap of etcd. I won't spend too much time on that. And then we'll dive down a little more into some components of how etcd serves and stores data. It's essential to understand that to be able to inform yourself when you're looking at error messages and logs and metrics to be able to make sense of what they're trying to tell you. We'll then spend a few minutes on some of the main tools that we use for debugging etcd, some of the things that have been really helpful for us, some things we've built or improved. We'll then dive into some techniques that we found to be most effective at getting from the initial issue report down to the cause of a problem. And we'll close out the talk with some proactive measures you can use to keep your clusters healthy. So let's just start with a brief recap of etcd. This is my opinion. You could say that etcd is a distributed key value store, and that would be true, but it doesn't really capture much detail about what we're trying to say etcd is. There are many distributed key value stores. Some are designed to store petabytes of data. That's not etcd's purpose. Another thing you could say about it is that it's a consensus data store. That refers to the fact that it relies on the Raft consensus algorithm to replicate the state to all the members of a cluster for high availability. But again, we're not totally getting to the intent of the system. So the way I like to think about it is it's a system to reliably manage the coordination state of a distributed system. So what we're really saying here is that we're going to build bigger distributed systems on top of etcd, and it's going to provide that core coordination. In the example of Kubernetes, it's storing all of your resource objects and providing a way so that users and the various components of Kubernetes can all interact with those resources to share state and coordinate their behavior. It's not the first of these systems. Google Chubby was an early example, and Apache Zookeeper is another major open source project which serves this purpose. And they share some common properties. They're designed to be highly available. They need to be because the distributed systems you build on top of them need that availability. They are being used for coordination, so they require a strong consistency model. And typically, the distributed system has many components in it, all of which need to observe some subset of the state in this store. And so there's usually some kind of watch mechanism that allows them to subscribe and receive near real-time updates to some set of that data so that they have fast access to it. Lastly, these systems typically include a variety of concurrency control primitives. So this could be a check and set operation to allow you to do optimistic concurrency control. It could be leases to allow you to build leader election, things like that. Just really briefly about Raft. This is a whole topic, and I can't cover it in this presentation and give it full justice, but Raft is the concurrency, is the consensus algorithm that etcd uses. And it's leader election based. So when you see things in etcd about leader election, we're talking about Raft. And the way that it basically works is that you require a cluster to have a majority vote on who the leader is. So if you have a cluster of size 3, the majority would be 2. And as long as 2 members can vote and agree on a leader, the system is available. One of those members could fail. It could be because it's been partitioned from the network or the machine has crashed, and the system will still continue to function. Sometimes, and so 3 is a common number of members in an etcd cluster that you would run. The other most common number is 5, because now you've gotten up to a failure tolerance of 2. That could allow you to have one planned failure. So for example, if you're planning an upgrade, you know you'll lose one member as you do that rolling upgrade. And then you can also, at the same time, support one unplanned failure and still be available. We'll talk about 3 major subcomponents of etcd throughout this talk. There's Prometheus, which is the metric system. So all of etcd's metrics are exposed through a metrics endpoint and are easily accessible as Prometheus. We're really happy about our use of that system. The major API endpoints are provided through gRPC. And it's also worth noting that if you want to explore those directly, they're re-exposed. In addition to the high-performance binary protocol, they're available as a JSON HTTP endpoint. And then the last major subsystem is BoltDB. etcd needs a backing store to persist its data to disk, and it uses this system for that. We'll talk a little bit more about it later. Let's talk briefly about how etcd serves and stores data. This is a sampling of a key space. This is from Kubernetes. And the key space is organized hierarchically. You can see that there are, the first prefix you can kind of ignore, but the second directory is the Kubernetes types, and then followed by the namespaces and the resource names. And Kubernetes chose this because etcd provides an index over the key space which is lexically ordered. And that allows you to do what's called a range read, which can get you basically anything that has the same common prefix, or anything that's in this example, anything that's in the same subdirectory. That allows you to, for example, here, you could get all of the replica sets with a single query, or you could get all of the replica sets for a particular namespace in a single query. Note, however, you could not get everything in the production namespace in a single query, because it's not all within the same prefix here. It's spread across multiple types. Here's a couple of the other major etcd operations to watch out for. There's a single write operation called put. Delete works kind of like the range read in that you can delete multiple entries in a single request if you need. And then there's an interesting operation called transaction. This is a multi-purpose operation. What it includes is a condition and 0 more operations that you are going to execute if that condition is true, and 0 more that you're going to execute if it's false. So, for example, you could use this as a check and set operation. You could say, if the value of some key is what I expect it to be, only then update it, which would prevent you from accidentally clobbering anybody else's rights. Or you could use it as a way of performing multiple operations atomically. You could just hardwire the condition to be true, and then you could put 2 put rights in that operation. All of these operations are what we call linearizably consistent. It's kind of a big word. Another term for it is external consistency. And if you're unfamiliar with that, that means I'll just give you a brief intuition. It's a fairly strong form of consistency where, say you have a client and it performs a put on one member in an etcd cluster. And then subsequently, it gets a response back acknowledging that that put was successful. It then does a read on maybe a different member of that cluster. Is it guaranteed to see the write that it performed previously? And the answer is yes. It's guaranteed to see its own writes, in the absence, of course, any other clients interacting here, because those are not atomic operations. So if another client jumped in and wrote in between, it could. But it's guaranteed to logically see a view of the world from after its own write. Those things happen in sequence. Another major type of operation that etcd has is a watch. This is a streaming operation. And what etcd does is it establishes a gRPC bidirectional stream with a server. And then it sends requests one way and receives updates in the other direction. So it can ask to establish watches over particular regions of the key space, and then it will eventually receive acknowledgements that the watch has been created, and then receive events for any changes to that region of the key space in order. This, of course, is eventually consistent. So just to follow through with that example, say we have a client, that client has a cache, and we've configured that cache to be updated using a watch from etcd on a particular member. But then if we were to, again, perform a write to a different member and receive an acknowledgement that that write's been completed, if we go to our cache, are we guaranteed to see that write? Well, no, there's a race, right? It depends. If the event processes through the system in time before our read makes it to the cache, then we are guaranteed, then we will see the write, but that's not guaranteed. It could be that the read happens first. So you need to be aware of those different consistency models for these different operations. I'm going to dive down into just a couple elements of storage, and we'll talk a little more about debugging. When debugging etcd, it's important to understand that it retains a global revision number, and every time you perform an operation, it increments that number. And it keeps the history of all the objects. So it doesn't do in-place updates of objects, it does kind of a copy on write mechanism. And we refer to this, this ability to keep a history and be able to read things in history as a multi-version concurrency control system. And that aspect of the system exists in 2 layers. The most obvious one is up in the etcd key space, where you can actually see the old revisions and where the watches can be replay history by traversing that history of objects. There's also a second, more subtle layer of multi-version concurrency control hidden down in BoltDB. This enables the storage layer to execute at least one read, or one write and as many reads as it needs concurrently. Most data systems would be exclusive. You could do one read or n write, or sorry, one write or n reads, but not one write and n reads. And it does that by keeping a history of objects that it compacts. Why am I telling you this? Well, this actually shows up in etcd when you're debugging it. There's 2 major operations that show up. One is called compaction, and compaction is the mechanism by which etcd goes through and removes old version of revisions once you no longer need them. You have to tell it what you want it to do. It'll keep everything by default, and you can configure it to automatically compact old revisions, or if you're using Kubernetes, the client will actually request the compactions automatically. In the case of Kubernetes, every 5 minutes it will request that everything's older than 5 minutes is removed, and Kubernetes is tolerant to not having a full revision history, so that works fine. Down at the BoltDB layer, there's some potential for fragmentation. This is less common in modern versions of etcd, but in 3.1 in particular, it was more common that we would see a database file get quite large, either because there were writes of different sizes, or at one point you'd reached a high watermark in size, and then etcd never automatically downsized the file. So there is an operation to defrag etcd, and if you see a large file and you're seeing poor behavior, one option would be to go through and defrag BoltDB using the etcd cuttle command. But beware that that is a stop-the-world operation. If you look at the etcd data directory, you'll see this, and you might get a little bit intimidated, but when debugging, this is a great way to get answers to questions. So I'm going to point out a couple things. One is that main DB file under snap. That is the main file that live reads are performed from. And then there's these snap files and wall files, and it's better to explain those through kind of a logical view of the system. So let's start with the wall file. The wall file stands for write-ahead log. If we were to create new files in the system, we might call them ceiling files or floor files. But this wall file, it's the first place a write happens, and once that write to the wall file is synced to disk, that write is now permanent. Of course, you can't really effectively serve writes from a file or reads from a file like that. So etcd immediately then also writes that to the main DB file, which is efficient for performing reads. Of course, etcd could crash between when that first write occurs and the second one does. So if it does, it's going to need to replay the wall file to recreate the DB file. That's how it recovers. There's another problem with this, which is that wall file would grow indefinitely over time, and that's not acceptable. So what we need to do is we need to keep it from doing that. And etcd does that by periodically introducing snapshots. It writes a copy of the key space to a file, it periodically associates that with the exact position in the log, and then if it needs to recover, it finds the newest snapshot, loads that, and then replays the remainder of the wall log to recreate the state. All right, now we have some intuition about some details in etcd. Let's talk about a couple of the main tools that we use. etcd cuttle is one of the most well-known tools, and it's actually pretty useful for debugging as well. You can use it to examine the state of a key space, see what's in there. Oftentimes when you're trying to understand why etcd is behaving a certain way under certain systems, knowing how many keys you have, do you have like 1 million jobs stored in a Kubernetes database and expensive rage reads against those, is that the problem? Just looking at the key space and glancing at it can be really helpful. But Kubernetes is efficient, it stores things in a binary protocol. So if you actually try and look at a particular object, you might run into trouble. You might see something like this. So we've written a tool called Augur. It's a pretty simple tool, and what it does is it allows you to examine Kubernetes objects in etcd. It's aware of all the Kubernetes data types, and you can easily just add it to that previous command that we ran and decode that back into YAML or JSON, whatever you want. That's handy. It's even more handy sometimes if, say, you have a user who accidentally deleted an object in a Kubernetes cluster. They might want that object back. One thing you could do is find the newest backup you have where that object hasn't been deleted yet, and use Augur to just directly extract that one object out of that backup file for them. It's a great way to remediate an issue without too many steps. The other tool I'll mention is called etcd dump logs. This is a great way to look at the wall file, the two main file types we had. You can see every operation that occurs in etcd in the order that they occurred. This can be useful for trying to figure out exactly what's gone wrong. We've even added a utility to this that I haven't shown here, where you can have it decode the value types using Augur. So you can see, like for example, we've got some severely escaped Kubernetes data in here. You could see that in a more readable format. And I will hand it over to Jingyi.
Cool. I got a mic. Thanks, Joe. So I'll talk a little bit about the debugging approaches. I'll first show you this graph. It's something I created when I first started working on etcd. I feel like I need some systematic way of debugging when a cluster is not functioning very well. So I started to create this debugging flow graph initially in my head, but now it ends up to become something like this. It's been useful to me, so I'm happy to share it with you. You can see, starting from the left side of the graph, it starts with some of these sanity checks, and as it flows towards the right-hand side of the graph, it leads you towards the root cause of the issue. So let's start with the sanity checks. Is etcd running? That's probably the first thing you want to check. There are lots of ways you can check. The first thing I usually do is, the example here, etcd is running in containers, so I'll just do a docker ps and grab the keyword. You can see the container is good. It was created 2 days ago, and it's been up and running since then. The next example is sort of like the bad example, where you can see it was created 2 days ago, but it's no longer running. Oh, by the way, so I highlighted issues or the bad examples in the red color, just for reference. Another check you can do is, so the etcd has the health HTTP endpoint check. If you're familiar with Kubernetes, you can use the kubectl, some people call it kubecontrol, get component statuses. etcd is one of the component, and you can see it actually queries the health endpoint of the etcd, and in this case, it returns health true. Alternatively, you can just query that endpoint directly using curl. Again, this is a good example. The last line is the bad example, where the client, or you cannot even talk to the server. You can see the connection refused. Some of the other checks you can do, this is etcd cuddle or etcd control endpoint status. What it does is it queries the endpoint the status of an individual cluster etcd node in a cluster. It is sort of like a weaker check as compared to the health check I just mentioned, because as part of the health check, actually, your cluster has to have a leader and it has quorum. As part of that check, it actually tries to do a quorum right. So for that to success. But this just gives you the status of the individual etcd node. Another check you can do is etcd control member list. It sort of gives you the view of from each etcd node in the cluster. So for example, when you have like bad connections between your etcd node, you suspect that there might be a network partition. You can use this to check each one's view of the cluster. So what might be the, so these are the possible outcomes after you run those checks. You might find that the server failed to start. If you follow the arrows, I think in most cases, it could be due to you have a bad configuration when you start the server, or it could be that if there's already a data file under your etcd data directory, when etcd starts, we'll try to read the file and catch up to state. If that file itself is bad, corrupted, then the server will fail to start in that case. Another possible scenario is that the server started. You can see the process is running, but when you query, for example, the endpoint health, it's not responding to you. And that could be like most possible reasons could be either due to simply a networking issue where you just cannot reach your server, or it could be that the server is overloaded and it's not being able to respond to you. Another possible scenario is that the server was able to start, you can see it's running, but then crashed. I'll give you an example here. If you look at the server log, I sort of highlighted in red the capital letter C. That means crash. When you see that in the log, it's a bad thing. And here it's an example where it's probably too much detail, but it's a free list corruption in the BoltDB database that's been used by etcd. If you're interested in details, I have included a link to the actual fix of that issue. Another type of sanity checks I usually do is to see if the space quota is exceeded. There are a couple of ways you can see that. For example, the first command, we just used that. It's etcd control endpoint status. So one of the field it returns is the database size. You can see here it says 8 gigabytes. That's the default maximum space quota allowed in etcd. If you see that, it sort of tells you you exceeded or you're reaching the maximum space quota. Or alternatively, you can just directly go to the etcd data directory and check the size of the DB file. In case your server is not running or is not responding to your query, the endpoint status query, you can just check the size of that file directly. There are a couple more places where you can see this issue. For example, if you do etcd control alarm list, normally if the etcd cluster is running correctly, there will be no alarms, but here it shows no space alarm. If you're issuing a command request from the client to the server and the server responded to you with an error that says database space exceeded, it basically means what it says. When this happens, usually you might want to do a compaction to remove the old history of your data, or you might want to do a defragmentation, and don't forget to disarm the alarm so that you can go back and running. Another type of sanity checks I usually do is to see if there are requests taking the server too long to respond. Couple of ways to see that. Indirectly, like we're using the same example, the same command, etcd control endpoint status. In this case, what happens is that your command actually times out. So there is a default of 5 seconds timeout for each of these commands. In this case, the server is not responding to you in time, so your command actually times out. Or alternatively, if you check the server log and search for the keyword apply entries took too long, you can see here's the back example where it's applying 1 entries but took like 12 seconds, which is really long. These are, I've listed 4 most likely next steps or 4 most likely reasons that could cause this issue. They are actually corresponding to the graph. If I just briefly go back to this graph, if you follow the arrows, there are 4 arrows, which are basically the 4 things I listed here. So one possible reason is that your request itself is too large, meaning you're reading a lot of things or you're modifying a lot of things. Another possible reason is that the server is overloaded. So your request might be small, but there are other large, expensive requests that's utilizing all the server resource. Another possible reason could be due to pure disk performance. A way to check that is, so etcd has this /matrix endpoint that you can use. It exposes lots of metrics. I've listed 2 metrics that are directly related to disk performance here. and it could be networking issue. So I think so far we've talked about all of the sanity checks listed on the left side. Now I would like to go through two things that I think, two debugging approaches I think are mostly common, mostly used. First one is trace the request. For example, you might start with the sanity checks and you found, oh, the space quota exceeded. Then you check the data stored in your etcd, and you couldn't understand why there were so many things stored in it, or you couldn't understand, remember each write request actually create a new version of the data instead of in place update. So you might found someone is frequently updating the data that uses all the space, but you don't know who's actually writing or updating that. In that case, you might need to trace the request. Another example would be you started from the sanity checks and you found, oh, one of the requests is taking too long to respond, and the request itself is actually really large. Like it's probably reading a lot of things and you don't know who is reading that. In that case, you also might want to trace the request. Here I have a concrete example of how to do the tracing. This is an example from the Kubernetes. So in Kubernetes, the only component that talks directly to etcd is kubeAPI server. So in this case, naturally we're tracing to the kubeAPI server log. So in the log, I'll describe what happens here. So it basically says there is a single request, take the API server 33 seconds to finish. And there are two major parts of this time. The first part is takes like 21 seconds, which is server reading stuff from the etcd. The next step is transforming those readings from etcd to the HTTP response, which is then sent back to the server client. So the first step is kind of problematic. You can see it takes 21 seconds for the etcd server to respond. And if you look carefully, closely, you can see the request actually reads 320,000 items from etcd in this single request. So this is how you can tell the request is very large. And if you want to trace a little further, the log actually tells you it is from a controller called cron job controller. So the request is from the cron job controller to the kubeAPI server, then to the etcd, which is a really large request. If you want to trace even further, you can look at the source code. I've included them here. You can see this line is actually calling the listing. So by the way, if you're familiar with Kubernetes, you can see this line probably can be optimized a little bit because this controller here, it's not using shared informer. It's just listing directly from etcd and is not using pagination here. This is an example of how do you trace the request. Another debugging approaches I want to talk about is inspect data. Joe actually already mentioned in the previous slides to use Augur to inspect data. Here, I guess I just want to emphasize that it's really important to remember there are like 3 dimensions in the database. How many objects do you have in your database? How big are those objects? And also, the third one might be not so obvious, but Joe already tried to emphasize on that, the revisions. So whenever you try to update an object, even though the object is already in etcd, but it will not update that object in place. It will create a new version or a new copy of that. So even though you might not have a lot of objects, and individually they're not so big, but if you're updating them very frequently, you can still use a lot of space. To be precise, the third dimension is the uncompacted revisions. So if you find the etcd is using a lot of space, you might want to better fine-tune the compaction parameters, try to remove the old revisions to keep your data size usage under control. This part I want to talk about the relation between the workload and the data volume. The workload, I mean the server request, like the example request we just saw earlier. So I think I I want to mention that the workload can increase data volume, like I just described. Each write operation creates a new version. And it might not be so obvious. In the reverse, data volume can also increase the workload. For example, if you have lots of stuff stored in etcd, and either intentionally or accidentally you're reading a lot of them, then it's creating a large request. This is the same example I just copied from the previous slides. I sort of highlighted different part. It's a list request. It actually requests to list all the job objects in etcd, but you might not aware that there are 320K job objects in your etcd. So accidentally, you might create a huge request. All right, so now I want to briefly talk about keeping your etcd healthy. These are some recommendations from us. First, as Joe mentioned previously, etcd support Prometheus, and I mentioned earlier, there is a matrix endpoint which you can use. We recommend that you monitor these metrics carefully, maybe select the ones that are most important to you and create a dashboard like this. We also recommend that you use the officially maintained versions. We're currently maintaining 3 minor versions, 3.1, 3.2, and 3.3. And there is a minimum recommended versions sent to the etcd dev mailing list earlier this year. Backups. We recommend you do backups for disaster recovery purpose. We also recommend that you do per backup check, meaning that whenever you got a new backup, you want to do some integrity check on that. If you're using the newer etcd control versions, you can just do etcd control snapshot status. As part of it, it will do the check for you, or because the underlying database is BoltDB, you can use, there is a command line tool called bbolt. You can also use that. We also recommend that you regularly verify you can actually restore your cluster from the backup file created. Upgrades. Again, we recommend you upgrade to the officially maintained versions. Upgrade itself is not trivial, but there is a well-documented process on the GitHub document. Downgrades, currently the only possible way to downgrade is if you back up everything before upgrade. But there is ongoing support for one minor version downgrade. If you want to track the process, it's in that GitHub issue. One last thing, it's very important. I think etcd community needs your help. If you want to help, there are some ways you can reach the current people who are working on etcd. I want to mention we have a community meeting where I think it's currently paused during the holiday seasons, but we're going to resume it early next year, early January. With that, thank you.
We have a couple minutes for questions. Yes.
What are the most common user-originated problems that you face, like too many keys, too big keys, and so on?
The question was, what are the most common user-originating issues we face? I would say probably the number one is creating way too many of a particular type of object. That is by far the number one. Question over here? Sorry, I didn't quite catch that. What's the recommended frequency of etcd backups? I'm not sure I can give one number to that. I think it's a little use case dependent. But I will say a couple things. Less than once an hour seems rare to me. And there are critical moments where you will most want backups. Right before you do an upgrade, probably right before you do a rollback, if you have to do a rollback from an upgrade. And the upgrade, I would include not only an etcd upgrade, but a system upgrade on top of it. So right before a Kubernetes upgrade as well. Yes, right here.
Even etcd and Docker container, observing the kernel level log
How do we separate noise from the logs? Well,
I don't think currently the etcd is emitting a lot of things into the log. Maybe you turn on the debug flag, I don't know. But usually, if you look at the starting from the line, you will see if it's information, which it's an I, or a warning, a W. Those are, I mean, worse thing is E, error, or even worse, C, crash. Is it taking too much space? Because otherwise, I mean, you keep all the logs and do a search, do a grab, and you will find all the errors and crashes. Yeah.
Yeah, fortunately, that is very greppable because right at the beginning, right before that pipe operator, you've got that single character that identifies it. So you could use that or write your own tool to pipe through it. I believe there are also some log level settings that you could toy with in etcd if you need, but that's typically to get more and not less. And I think you want less, so you might want to just pipe it through a tool that filters if that's what you need.
I had one question or comment.
Sorry.
On your diagram where it showed the etcd server not running, we had a cluster that was healthy for probably 8 months to a year, and then it started dying, and we found out that the Docker container had a memory limit that apparently the etcd had grown to the point where it hit that memory limit, and Docker was killing it as out of memory. And so that might be another thing to add to your triage by just changing the upper memory limit for the Docker container. It started up and it was perfectly healthy. So that was kind of a surprise where everything was working just fine forever. Nothing changed, no upgrades, but it started crashing.
Great.
No, but thank you. Think that that is useful. Question over, oh, sorry, was there somebody else?
I think he wants to be asked. Right. Uh-huh.
The question was for the disk too slow. How do you know if your disk is too slow? What could you look at? How would you learn more about that?
Go ahead.
Yeah, I would say the IOPS metrics are one of the great things to watch. If you see that latency reaching a limit there, that is a pretty strong indicator, and that's a metric that you could alarm on, that you've probably exceeded the limits of your disk. There's also an additional section. Yes, there is. I don't remember it off the top of my head, but I can tell you where to look for it. I believe if you search the for etcd.
It's on GitHub document. Yeah,
yeah
there is specific hardware recommendations.
Yeah, it's either in the FAQ or the recommendation operational guide. There are very specific mentions of that. Great. One over here.
Comment.
Yeah, the question was, you can create a lot of pods in Kubernetes, and that can end up overloading etcd. Is there work being done to improve things like this? The answer is yes. That's why some of us, or both of us actually, are committers on both projects. In that specific example, the pods send heartbeats to Kubernetes, which puts load on etcd. There is an alpha status fix to move that out into a separate object that is much cheaper to update. And that's really how we fix some of these things. We could try and get more capacity out of etcd and improve its scalability and performance, but if the load that's coming to it is unreasonable, we need to go back and improve that load, absolutely.
Do you have any recommendations for managing backups?
Right now, the tools that etcd Cuddle provides, the direct tools, seem appropriate. If you are using a toolkit like, you know, etcd operator or etcd admin, then I would look to their documentation on what they recommend. But those are the correct backups to take.
I think it's a built-in to the log. When there is a very long request of the API server, it will show the tracing. Yeah.
You can reconfigure the Kube API server to compact more often if you need. You can also do your own manual compactions, but I would kind of recommend, if you're using Kubernetes, to work with it to do the compactions. It can tolerate the loss of historical data, so it should be safe, but I've never done it. No, sorry, one more here.
When I do consecutive snapshots of a Kubernetes cluster that I'm not making any changes to, the number of objects varies like widely, grows and then shrinks. Do you know what's causing that? What's the objects that are getting created and revealed?
The question was, sometimes when taking snapshots, some snapshots can be widely larger than others, and it's not clear why. Well, one of the reasons is if you do a snapshot right at the tail end, right before compaction happens, and there's a lot of activity in that cluster, there could be a lot of revision counts. And then if you did one right after the compaction happened, you could see a drastically lower number, because it's, you know, if you're doing it every 5 minutes, removing everything older for 5 minutes, that could be a 2x interval. And if you're doing something different, it could be even bigger. I'll take one more here, and then we'll talk after. Yes, large compactions can get expensive. There's been work to make those increasingly concurrent, but I would still say that is not an entirely solved problem in etcd. Making those fully concurrent and low priority so that they're completely invisible is an aspirational goal that's not been achieved. And yeah, so if you are seeing large compactions, you will see them written in the logs, and you will see how long they took. And you may see latency spikes that are visible up through the system from there. So I would keep an eye on that in the logs. We'll take more questions after. Thank you, everyone.
Thank you.